Hey everyone, one of the ideas that came up in the Whisk forum that someone asked about is what if you charge two capacitors and they have different capacitances and you connect them but not like we talked about when we did connected capacitors. When we did them in parallel, we had one charged and one uncharged. What happens when they're both charged? So what I did here is I have two capacitors. You can see that one is larger than the other, and I charge both capacitors to 9 volts. So I can show you with the voltmeter here that both of these are at 9 volts. So what happens when I connect two charged capacitors together? Well, I take one wire and I put it here. I take the other wire and I put it here. And what happens? If you look, the voltage is still 9, and the voltage here is still 9, which means nothing happened. The reason that nothing happened is because they're technically at the same potential, and both sides of these parallel plates are positive and the other sides are both negative. So no charges have the need to move at all. They are at the same potential and they have the same sign of charge on them, so nothing happens. But we can take this one step further, which I think is what someone was asking, is what if I turn this capacitor around and now I have the negative plate touch the positive plate and vice versa on the other side. They're still the same voltage, but do charges actually move now? So let's try and set this up and see what will actually happen. So here's our setup. I've just turned the capacitors around now, and I'm going to connect the positive side to the negative side and the negative side to the positive side of each of the different capacitors. They're both at 9 volts, and I know their capacitances. This one is a 0.1 farad capacitor, and the other one's twice as big. I try to represent that with twice as much charge. So it's a 0.2 farad capacitor, which means the charge on this one up here is 1.8 coulombs, and the charge down on this one is 0.9 coulombs. Now, what we need to think about this time is that we don't have the same signs of charges attached to each other. So when I connect these two together, I have excess positive charge. I have 1.8 coulombs of positive charge. On the bottom plate, I have negative 0.9 coulombs of negative charge. So there is a charge imbalance, and so the charges are going to try and come to a balance even though we're at the same potential. Now, we're at the same potential from high to low, but technically since the capacitor is backwards, you could see that there's a difference in potential of positive 9 and negative 9 volts. So maybe that's the reason charges want to move. But what I could see is that really the net charge between those two plates that are touching is a positive 0.9 coulombs. And over here on the other side, this is a negative 0.9 coulombs. That is the net charge. And when we connect those two, so ready, set, and go, charges have now redistributed themselves. You can see that the excess that was positive has made this plate that was originally negative positive, and the same thing happened over here. So now that they're connected, they look like they're connected capacitors in parallel, and there's our final setup. So the question is now, what is the voltage across both of these? Has the voltage changed since the charges redistributed themselves? Well, the way that I can kind of visualize this is that they went to a net charge of 0.9 coulombs, and I know that now they look like they're in parallel, so I can look at the total capacitance as C1 plus C2, or 0.3 farads. So if I want to know the common voltage that they're going to come to, I can take the Q over C, and when you get that, you should get around 3 volts. So let's check that with a sim. I take my voltmeter and touch one side of the capacitor, I get negative 3 volts, and touching this side I also get negative 3 volts. Negative because the charges have switched sides and I'm reading from low to high instead of high to low. So we do get to the same voltage. Now what does that mean for my charges? Well, if they're both at 3 volts, I know their individual capacitances, I know their voltage now, and if you solve for the charge, this guy has a charge of 0.3 coulombs, and this one up here has a charge of 0.6 coulombs. And if you look at that, if I take a 0.6 plus a 0.3, what I do end up getting is a net charge of 0.9. On either plate, the positive plate or the negative plate, they add up to 0.6 or 0.9 coulombs. So that's how you can kind of reason through that problem. But the one that's in the homework there is a little bit more tricky. So what we have here is I have 3 capacitors. They're all different capacitances. One's 0.1, one's 1.15, and one is 0.2. And I'm going to charge them all independently. And I think your homework problem has them all line up in parallel, which means everybody's going to get the same volts. So I'm going to give everyone 9 volts of potential. Okay, so here's our setup here. You can see that I've charged each of the capacitors. They're all 9 volts. I can take my voltmeter and show you the potential. So I get 9 volts across this one. Ooh, I got 18 volts now. That's because I'm across 2 capacitors, and I've got 27 volts across all 3. And it looks like they're all in series, but you've got to be a little careful on this one. There's no battery connected to it, so there's no ability for the battery to add more charge to one than the other. You can see since they're all charged to the same voltage, they all can have different amounts of charge. The 0.1 you can see has less charge than the 0.2. But when we connect them, that's what we want to know what happens. When I connect these all together, how do I get the final charge and the final voltage? Watch what happens now. So a lot of things just happened right there. The plates have switched signs. Some of them have become negative when they were formerly positive. And you can see that I actually have 2 positive plates pointing towards each other right here between the small capacitors. At the ends of the large capacitor and the small capacitor, I see both those plates negative. So what in the world has actually happened here? Let me try to draw this out and give you some hints. Now in the problem, in the homework, there's a switch here, because right now that's when the charges will actually move, when the switch closes. So before the switch is closed, you can see C1, C2, and C3. And I'll use the values from the FET simulator. You're going to have a different setup in your homework. But C1 is going to be 0.1, C2 is 0.15, C3 is 0.2 farads. So there are all their individual capacitances. Since I know they're all charged to 9 volts, with 9 volts, I can tell you exactly how much charge is on every single capacitor. The first one is going to have a Q of 0.9 coulombs. Second one is going to have a charge of 1.35 coulombs. And the last one's going to have a charge of 1.8 coulombs. So you can see that every capacitor has a different amount of charge, and each of those plates are touching a different amount of charge from their positive to their negative side. If we look at this side versus this side, if I look at that net charge when they do become connected, I see a plus 0.9 coulombs attached to a negative 1.8 coulombs. So the net charge around that outer ring there is negative 0.9 coulombs. How about the connection here? I've got a negative 0.9 and a positive 1.35. The difference in charge there, about 0.45 coulombs, and the difference between these guys here, the 135 negative and the positive 1.8, is also about 0.45 coulombs. So how can we set this up? What is actually going to happen when we do this setup? Well, one thing that we can say is we can look at how each of the capacitors are slightly different from each other. If we want to treat them as series, we can, but let's remember the rule for series, that the voltage must be shared among them. So the voltage for the first capacitor plus the voltage for the second capacitor plus the voltage for the third capacitor must equal the total volts of the system, or from the battery. Remember, a battery is not in this now. Since there's no battery, we're going to say that the total volts has to equal 0. So what can I say then? I can say that Q1 over C1 plus Q2 over C2 plus Q3 over C3 must equal 0. So now we have to go back to about how much charge is on each capacitor. Let's say that charge 1 is just going to equal Q. That'll be the charge on the capacitor initially. So this Q is always going to be 0.9 for us. But I've got Q2, which is different from Q3, and to solve for the charge on each capacitor, what I'm going to need is a common variable in terms of charge. So there's a little trick we can do here. We can say that, okay, charge 2, 1.5 times the charge on capacitor 1. And Q3 is going to be twice the charge on capacitor 1. Why do I know it's twice? Because the capacitance is twice as big. And 1.5 because it's, again, just a little bit bigger than that first capacitor. But here's the little trick that you can do. To write Q2 in terms of Q1, here's what we can write. I can write the charge on Q1 plus an extra half Q. And why is it an extra half Q? Because remember, the capacitance is a little bit bigger. Let's write Q3. Q3 is going to be the charge on capacitor 1 plus one extra amount of charge. So I can write it as Q1 plus an extra Q, again, since the charge is twice as much. Now I can rewrite my formula from above as Q1 plus half Q. And over here I can write this as Q1 plus just another Q. Since I know each of the capacitances, I can put those both all in here, and I can solve a ratio for Q1. When you do all your algebra, you should end up with something like this. You've got Q1 over 0.1 plus the quantity Q1 plus half Q over 0.15 and Q1 plus Q over 0.2. Look at the problem that you have and see how each of your capacitors compare to each other. Are capacitor 1 and 2 twice as big? Are capacitor 1 and 3 times as big? So your little ratios here that I've written might be a little different based on what we set up. When you solve this all out, you'll get a fraction of what Q1 is. Q1 for me ends up being negative 0.38 times the initial charge. That's the charge on capacitor 1 before we ever set this up. So for me, this is 0.9 coulombs. And if I take 0.9 times negative 0.38, negative 0.342 coulombs of charge on this left capacitor here. So you can see that left capacitor plate became negatively charged. So I know I got the charge right. And if I take the charge times the capacitance, you can see I'm getting a voltage of negative 3.42 volts. And now that you know the charge on one capacitor, you should be able to stretch that out through all the capacitors. I'll show you the answers for the FET sim that I have here. The middle capacitor goes to 0.69 volts, and the last capacitor here goes to 2.769 volts. In the end, all the voltage adds up to 0, but they're all redistributed. So since I know the charge on that left plate here is negative 0.342 coulombs, and I know that the connection between these two outer plates here was a negative 0.9 coulombs, I should know that the charge on this plate over here has to be the sum of that net charge. I should have 0.558 coulombs of charge on this plate. That would be negative on the right plate and positive on the left plate. And from that, you should be able to go through and figure out the charge on each capacitor. Once you know each of the charges, you should be able to go through and solve for your voltages. So I hope this helps, and we'll talk to you next time.